Let's move on. So that's just the linearization equation, right? But what about if we actually want to get some sort of wave solution, okay? Well, we know from before, again, here comes the ansatzes. Maybe this is still making you uncomfortable that we just use an ansatz out of thin air. Let me just say again, the way ansatzes work is that you suspect that you have a solution of a certain form, and so you try a solution of that form because it will make your equation simpler. If you can then solve the resulting equation and get a solution, then you have proved the existence of a solution of that form. If not, no harm done except for maybe some time wasted, right? But it's a perfectly valid way to obtain solutions to PDEs. Okay. All right. So let's try our ansatz. Okay. And for some reason, I'll take S for speed again. I think it's because maybe that's what Shear and Levy use. A lot of people use C though. Okay. All right. So in order to look for a wave solution, let's do a couple of different additional things, right? We'll also assume that these are traveling pulse solutions, right? You can go ahead and try and assume traveling front solutions. If you try that approach, you will, I think, not find traveling front solutions. So it's a traveling pulse. This is like, these are also called solitons, especially in the case of the KdV equation. So what does that mean as far as our assumptions? It just means that at the boundaries, V is going to be 0, and V's derivative is going to be 0. Okay. So again, these are boundary conditions, although they may be a bit peculiar to you because they're at the limit points. Okay, or the infinity limits. Okay. All right, fine. So let's substitute this ansatz in, and we'll integrate. Okay. So I'll just go ahead and start by substituting it in. So first of all, I get minus S V prime plus V prime plus gamma V prime equals 0. If I integrate this, then I get minus S plus V squared over 2 plus gamma, oops, sorry, I forgot a prime there, V prime, okay? And this should equal a constant, right? But I can take the limit of this. If I take the limit of this at positive or negative infinity, right? This, sorry, missing something there. These terms should go to 0, and I would get gamma V prime equals some constant out at infinity. Okay. And so in order to make sure that my my solution is vanishing really out at the boundary, I need this constant to be equal to 0. Okay. Essentially to satisfy my boundary conditions. Okay. So taken all together, this is our equation I'll call star here. And the approach now is to convert this to a phase plane problem back from your ODE class, okay? So you can rearrange things, right? We can write this as V prime is equal to what? So I get S divided by gamma V minus 1 over 2 gamma V squared. I can equivalently write this as the following. So I get V prime is equal to W, W prime is equal to 1 over gamma, and then I'll write it like this, minus V squared over 2 plus SV, okay? Now, what do you do with phase plane problems? Well, back in your ODE class, you start by finding the equilibria, the nullclines, look at the stability, try and understand the trajectories that live in this space, okay? What has happened here? Well, we've converted a PDE into an ODE, and the solutions to that ODE should be the shape of the traveling wave solutions that we're looking for. So the question is, can I get a trajectory in the phase plane that looks like it should in order to satisfy my boundary conditions, okay? That has the right shape, okay? So we're going to look for that. So we have to sort of deal with the phase plane though as it is and use the techniques that we can for phase planes, okay? So to look for a traveling wave solution, okay, first look at the, this is called the local stability, right? The stability around fixed points, Jacobians, and all that good stuff of equilibria, okay? So we can do that, no problem. So equilibria of this problem, anybody want to tell me what those are? The restriction on W should be easy. In order to have V prime equals 0, W equals 0. In order to have W prime equals 0, I need what? Well, this right-hand side to be 0.
SV equals V squared over 2.
Right. So we can solve that, right? And we get V is equal to I'm skipping ahead. Maybe I should. Am I going too fast?
V squared over 2S.
Yeah, right. So V squared over 2S, okay, or V squared equals 2SV, or V is equal to 0 or 2S, okay? So these are our two nullclines, right? So our V nullcline is just W equals 0, and our W nullcline is V equals 0 or V equals 2S, okay? So I can draw all this out, okay? And my intersection points are going to be at 0, 0, and then 2S, 0, okay? So let's draw that. So if I draw my phase plane right here, I'm going to draw W, and here I'm going to draw V. Here's one of my nullclines at V equals 0, right? This is a nullcline W prime equals 0. Here's another nullcline. This is another nullcline W prime equals 0. Here's my V nullcline W prime equals 0, okay? So I have two fixed points here and here. I'll fill in the one that is stable, okay? So my fixed points are just going to be V and W equal 0, 0, and 2S, 0, okay? Let's look at stability. Well, for that, I need a Jacobian, right? So my Jacobian of VW is just going to be the V and W derivatives up here. So I have 0, and 1, okay? And then down here, I'm going to have, let me write this out. So I get S minus 2V divided by gamma, and then 0, okay? Then the eigenvalues of my Jacobian are going to give me my stability in this case. Okay, so sorry, this should not have a 2 in front of it. S minus V over gamma. Okay, so my stability then at 0, 0 is given by J equals what? 1 S over gamma 0, okay? So I get lambda squared minus S over gamma equals 0, or lambda is equal to plus minus square root of S over gamma, okay? So that means that my fixed point 0, 0 is a saddle point, okay? So that means I have some directions that come into it along which it's stable, and some directions along it that are unstable, okay? Something like that, okay? So what about my other fixed point, okay? Let's look at that. So my other fixed point is 2S 0. In that case, J is equal to 0, 1, and then if I have S minus V in that case, I'm going to have minus S over gamma 0, okay? So my eigenvalues in that case are going to be given by lambda squared plus S gamma equals 0. So that means that lambda equals plus or minus I, the square root of S over gamma, which means that I have a center in that case, okay? So let's then try and draw essentially what's happening in this. So let me redraw our phase plane here. This is V, W. Here's our center here, and here's our saddle, okay? And if I look up here, okay, V prime equals W, W prime equals 1 over gamma. Let me just kind of rewrite everything so that we can take a look. S times V minus V squared over 2. Okay. So right here along V equals 2S, right? This is one of our W prime equals 0. Okay. So if W prime equals 0 there, if I want to look at how V is changing, V should be positive. V prime should be positive up here. So trajectory should go this way. V prime is going to be negative down here. So if I want to know what direction the oscillations around the center are moving, I can just look at this. If I look over here, right, along where V prime is equal 0, I see that when V is greater than 2S, this whole thing is going to be negative. So trajectory should go this direction on this side and this direction on this side. So that gives me the circulation of the oscillations around the center. Okay. And I can do a similar accounting essentially for the direction of the flows over here. I won't belabor that. I'll go ahead and jump to the punchline, which is that the trajectories in these quadrants flow away from the fixed point, and the trajectories coming in from these quadrants tend to flow towards the fixed point. So that, when you're out here, you have this sort of these saddle-shaped trajectories. When you're out here, you have these saddle-shaped trajectories. When you're over here, you have these saddle-shaped trajectories. And when you're over here, you sort of turn a corner and you join the, circulating, oscillating solutions here. Okay, around this trajectory here, these limit cycles. Okay. Now, something should happen though, okay, where at some point a trajectory gets large enough that it should pass through the saddle, right? If we just keep growing these trajectories here, right? They should eventually be large enough that they would pass through this saddle point. And at that point, you have what's called a homoclinic orbit, okay? So this particular trajectory here is what's called a homoclinic orbit, okay? So same line orbit, okay? So the idea is that you start and end the trajectory at the same point, but there is a start and finish to it, unlike an oscillation, okay? And if you think about what this means, go ahead.
So maybe this is obvious, but you sort of drew these, what you're calling orbits, as like closed periodic loops. Is there reason for us to suspect it would actually be that way? Or I buy that they would circle around the center point, but would they necessarily start where they finished?
Yeah, because otherwise you're going to have trajectories crossing, right? Because you know that they don't spiral into the point, and you know that they don't spiral out of the point. If you don't have them all sort of, stacked like concentric orbits, then you're going to have trajectory crossings.
Well, couldn't they spiral to a limit cycle?
But this is a homoclinic orbit. It's
Oh,
not
okay.
it's not a limit cycle, right?
Okay.
Yeah, if you had an outer limit cycle, then you could, but yeah. I've been a bit hand wavy about it, but yeah, that's the shape of things. Okay, so what I want to say about is there good any other questions? Yeah. Let me just say then that this homoclinic orbit, it has all the things that we need for a soliton solution. It starts out at v = 0 and it ends at v = 0. Okay. And remember that, you're probably used to phase plane analysis where your independent variable is time. Our independent variable in this case is psi, right? So if I flow forwards in time, if I flow forwards along a trajectory, I'm going all the way to psi goes to infinity, right? Psi goes to infinity as I move in this direction along here. Back here, right, this is where psi equals -infinity, okay? So essentially, I have this homoclinic orbit here, and that is the shape of my soliton solution that I'm looking for. So I've made an assumption, and I have shown that I have some trajectory in here that will work. What are these solutions here? Okay, so this is my soliton solution. Okay, these are, and I always say this wrong. These are our conoidal waves. Can never remember if it's conoidal or sinoidal, okay? And essentially, these are periodic traveling wave solutions. Okay, so even though those aren't what we were looking for, we discovered them by sort of unfolding this phase plane analysis. Okay, So our soliton solution is our solitary traveling wave solution, okay? These conoidal waves are, if you think about what they look like, they're just going to be basically water waves that go up and down, you know, just like waves rolling in on the beach towards you, one after the other, right? So
didn't we enforce the vanishing boundary conditions already? Or would
right. So that was one way that we could rid ourselves of that constant. But in this case, you can also you know, make the corresponding assumptions for these conoidal waves and also kill off that constant. Just sort of making, yeah, it's a more complicated argument because you're talking about a periodic solution as it goes out to infinity. But yeah, you can make the right restriction to kill off that constant. All you need is something to kill off that constant. So here's our soliton, right? And it's going to look something like this. It's going to start off with at 0, right? And then at some point, V is going to be, well, V is going to be positive the whole time, but V prime is going to be positive. And then out here, right, it's going to peak. So V prime is going to be 0, and then it's going to fall back down. So our soliton solution looks like this, okay? And S is actually parameterizing which of these curves that we live upon, right? So each of these curves is a different value of S in this case. Well, sorry, no, that's not true. This is a particular phase plane for different values of S, right? So the one that we've drawn here is for a particular value of S, and that will be the speed of the wave that you have, okay? Our periodic traveling waves, okay, or conoidal waves are going to look like this, right? They're going to be just these rolling waves, okay, that repeat in their shape over and over again. Maybe more like these periodic sort of waves that we talked about in the linear analysis, okay? And so those are also going to travel with some velocity that's given by S, the particular parameter that you've used to construct this phase plane. Okay, so they're going to flow to the right as well. Okay, I think that's all the time we have for today. So hopefully I've unpacked a couple of things for you today. First of all, this linearization analysis in order to look at dispersion relations for nonlinear wave equations. And then the second piece we talked about is going from nonlinear PDE to nonlinear second order ODE, converting that to a phase plane, and then using a phase plane analysis to extract these different traveling wave solutions. So this idea of finding either a homoclinic orbit, or in the case of a traveling front, it would be what's called a heteroclinic orbit, where you start and you stop at a different value of V. So that would be like the back and the front of the front, is what allows you to find these traveling wave solutions in the projected equation. Okay. Questions about this? All right. I think you might have some KdV analysis on the homework. I can't quite remember. So on Friday, we'll